Hi, we are Group 8 presenting the final video for the Computer Assistive Robotic Eating System. Our team consists of 4 computer engineers, Queenly, Shani, Bao, and Twin. Now to talk about the problem we are trying to solve with this project. So as you know, eating is something we do every day without thinking too much. But for people with disabilities, it is a real challenge, so many of them heavily rely on caregivers for assistance during meals. Our project combats this challenge by developing a more affordable and accessible solution that can help people with upper body disability be able to eat more independently, increasing their quality of life and reducing caregiver workload in both the home and healthcare settings. Now that we know our motivations, we establish a few key goals for this project. For our basic goals, we focused on developing an assistive feeding arm that is easy to use, reliable, and also capable of accurately acquiring food during each feeding cycle. Our advanced goals include a safe system shutdown in unexpected situations and an app that tracks all the necessary statistics for dietary health monitoring. This slide shows the overall image of our entire robotic feeding system. One of the main subsystems is the MyCobot 320 Pi robotic arm, which was provided by the Nimbus Research Lab. Inside of this, there is a Raspberry Pi 4 which controls any of the low-level motor coordination of each axis of the robot. And then there's the main subsystem, which is the Jetson Orin Nano. This deals with all the heavier computing processing, including the computer vision and real-time updates between the time-of-flight sensor. Attached to the Jetson Orin Nano are 3 foot pedals, which the user can operate by their feet. The first button will allow the user to initiate the feed. That will go through the whole sequence of scooping the food and going to their mouth and feeding them. The second button will be a selection button, and this will allow the user to choose between 4 sections on the plate and have a variety of food selections. The last button will be an emergency stop button, which allows the user to stop the robotic arm at any moment if they feel uncomfortable with the movement and if they need to readjust. Connected to the Jetson Orin Nano is an LCD which will give the user real-time live updates of the state of the robot, whether it is in the feeding phase or whether it's in selection phase or emergency. It will also show the user clearly what selection they are currently on so they aren't confused. Then on top of the robotic arm, there is the camera. This is connected to the Jetson Orin Nano and provides all the visual input, which allows the Jetson Orin Nano to run through all of its computer vision algorithms. Along with the camera at the top, there is a time-of-flight sensor which gives real-time updates of the depth between the arm and the user to allow for safety features. Lastly, there is a April tags attached to each corner of the plate, which is separated into 4 sections. These April tags allow us to calculate the coordinates and locations of each section of the plate and translate that to robotic arm movement. Here is footage of the hardware system set up in a real-life environment. You can see all the pieces mentioned in the previous section and how it is wired and connected and actually placed on a table for the user. Our software is split into 3 systems, one for the mobile app, the second for the Raspberry Pi motor controls, and the third for the Jetson Orin Nano high-level controls. The software setup of the mobile app includes full communication of the front end and back end. Firestore allows for real-time synchronization with the robotic system and app. This file on the Raspberry uses Elephant Robotics Pi MyCobot library and the MyCobot 320 class to control the arm. We use joint angles for reliable home positioning, angular coordinate movements for larger motions like plate viewing and scooping, and linear coordinate movements for smaller mouth tracking corrections. The Jetson sends commands over the Ethernet, including selected plate section, mouth position, and time-of-flight approach commands. The Raspberry then converts those requests into bounded steps and predefined trajectories, so the Jetson decides where to move while the Pi handles how the arm executes it. For the April tag subsystem, this file processes the camera frame, detects each tag, and extracts its ID and image coordinates. It saves those results in this file as the most recent calibration data. And this file manages when the scan runs, including the time-of-flight plate height reading, and verifies that the calibration succeeds. Then this final file matches the selected section to the correct tag and converts that saved data into the scoop target used by the feeding cycle code. For the YOLO subsystem, we trained separate plate and spoon models using over 500 annotated full and empty examples, reaching about 99.5% MAP. The original .pt models caused frame lag on the Jetson, so we converted them to TensorRT engines for faster GPU inference. This code checks several frames, keeping the highest confident results from each one, and counts whether each food is present or empty. Then this code turns those votes into a pass or fail decision. The plate is checked before scooping and the spoon is checked afterwards, so the robot only continues when each vision gate succeeds. For mouth tracking, the feeding cycle file uses media pipe to calculate the mouth center and compare it with the camera frame center. The resulting horizontal and vertical errors are sent to the Raspberry Pi as align commands. To reduce the arm moving back and forth, we added command pacing, correcting only the largest error direction and requiring the mouth to remain centered for several frames. Once alignment is stable, the time-of-flight subsystem provides the forward distance and controls the final approach. The feeding cycle only continues when 3 conditions are met: when the mouth is detected, when the time-of-flight reading is valid, and when no emergency is active. A consistent number of stop distance readings are required before the bite timer starts, and any loss of tracking, invalid distance, or emergency immediately stops forward motion for safety. For physical controls, this file reads the select, feed, and emergency stop inputs and uses software debounce, so only stable button presses create events. Those events are passed to worker.py, where select handles calibration or plate selection, and feed only starts a bite when calibration is complete and no other cycle is active. The emergency button follows a higher priority path. It latches the emergency state, interrupts any active process, and causes worker.py to stop the arm, block other inputs, and begin recovery. We also added a rearm gate because the emergency sequence was sometimes triggering twice. The button now has to be released and remain stable before it can trigger again, while emergency notify sends the caregiver alert independently, so local stopping still works even if the notification fails. Worker.py is the main coordinator on the Jetson. It receives commands from the app and physical buttons, checks that the robot is calibrated and not already feeding, and also not in an emergency state. Then it sends those requests to each of the correct subsystems. It also claims Firestore commands before executing them to prevent duplicates. Overall, Worker.py does not perform the vision or the motion algorithms itself. It keeps the April tag, YOLO, feeding, button, motion, and notification subsystems running in the correct order without conflicting. Behind Worker.py, the shared session and status modules keep the selected plate section, calibration status, feeding state, GUI, and Firestore updates synchronized. This ensures every subsystem is working from the same current robot state. For our basic full cycle demonstration, the caregiver will set up the app to start recording meal statistics. The user will then utilize the buttons to go through both the initialization phase and feeding phase. In the initialization phase, the computer vision will check the April tag for plate orientation and decide whether the plate is empty or not. Once it verifies there is food on the plate, in the feeding phase, the arm will go through a scooping motion and align the spoon to the user's mouth to successfully finish the feed.
Grandma, are you ready to eat?
Yes.
Okay.
Here, the caregiver will indicate to the app that the feeding cycle is beginning in order to record the important statistics of the whole meal. The user will click the select button to initialize the plate's orientation through reading the April tags. Then, using a YOLO-based computer vision system, the camera checks whether there is food on the plate. After the arm successfully reads that there is food on the plate, it will go into the feeding phase, where it will scoop from the user's selected section. Once the spoon scoops, the computer vision will do one last check to see whether the spoon successfully acquired the food. The final feeding stage after the spoon has food on it is the alignment, where the spoon lines up with the user's mouth on the X-Y axes and then proceeds to start going towards the user's mouth to allow for easier eating reach. Once the time-of-flight sensor reaches a certain close distance away from the user's mouth, a countdown starts to allow the user to bite the food before it goes back into a default position, allowing the user to begin another feed. In this video, it says 3 seconds, but the caregiver has the option to change this length of time within the app. When the user is fully done with their meal, the mobile app will notify the caregiver to allow the care system to be packed up and cleaned up. The app UI gives us a variety of statistics useful for patients' records to pass on to medical assistants or appointments the user may already have. The data that is live updated with the app include whether the Jetson can communicate with the app, the last robot update, whether the plate or the spoon is currently full, the current robot state, the number of bites the user has taken in this meal, the lifetime number of bites, the current section the user is on, whether emergency state is activated, number of successful feeds, failed feeds, feed button presses, whether eat is pressed, whether stop is pressed, and the time of the last feed. For our more complex scenarios, we demonstrate 3 storylines. The first one is when the plate is empty. In the plate empty scenario, Grandma finishes all her food but still wants to continue eating. Here, the computer vision uses our trained YOLO model weights to identify that the plate is empty and sends the caregiver a notification on their phone so they can be called over and fill the food for them. After the caregiver refills the food, Grandma can reselect the section they want to eat from, and the computer vision will successfully view the plate as refilled and continue with the scoop. The second scenario is when the spoon is empty after a failed scoop. The purpose of spoon empty is to decrease unnecessary movement towards the user in the situation that the robot did not successfully acquire the food on the first scoop. Grandma will then be instructed to press feed again to allow the arm another chance to scoop the food and try a new section that is more full. The last scenario is the emergency stop scenario. For this, we acted out a situation where Grandma cannot continue the feeding due to needing water, so she clicks the emergency button. Here you can see the notification that gets sent to the caregiver during an emergency stop. From here, the caregiver can go and help assist Grandma in whatever she may need. And then after 10 seconds, the robotic arm will go back to a default position. To demonstrate our system specifications, we will show you our end effector positional accuracy, the success rate of our food acquisition on the utensil, and the latency of our mouth detection algorithm. In this snippet, we use visual indicators on the view of the camera to show the distance between the center point of our camera in comparison to the mouth it is trying to align to. We do 10 more trials of this process and receive an average of a 4.85 centimeter difference. For food acquisition, we cycled through the available 4 food portions and scooped from each section, observing whether our spoon successfully acquired the food. Our goal was to get about a 70% or more success rate. Our result was about an 80% success rate when scooping through our different plate sections. Our goal when measuring the latency of mouth detection was to be less than 10 seconds. To demonstrate, we printed out the average time it took to detect our mouth over a course of different movements and angles. The results showed us a much better outcome than we expected, with the mean average being about 13.88 milliseconds and the standard deviation being 3.58. Because of the good results in the future, we can update our specification to be less than or equal to 0.1 seconds, which is based on human visual reaction time. Our current project scope limits the food scoop to one size. For future editions, the scoop will accommodate various scoop trajectories for different types of food. Through this project, our team has learned to hone our skills of computer vision, robotics, and system integration, along with improving our communication and time management together. That is all for our presentation of the Care Assistive Feeding System. Thank you all for listening.